All right, so today we're going to talk about something called relative velocities. Okay, and relative velocities are basically measured velocities or really observed velocities from a different frame of reference. Okay, and I know that's a little bit hard to wrap your brain around, but relative velocities are basically ideas like a bird is flying north and the wind is pushing them east, so really what direction are they flying, right? Do we see that kind of shift, right? If I'm flying north but my wind's pushing me east, I'm going to really be kind of flying in that northeast direction. That's essentially what relative velocities are, okay? So that if I was standing on the ground watching this bird fly, I would really see him traveling kind of in the northeast direction. Whereas he's trying to go north, the wind is pushing him east. Really, to me, relative to the ground, he's got a velocity in the northeast direction. That's essentially what relative velocities are. Okay? You don't have to write the example down. I just want to talk through it a little bit. All right, so if I've got two trains traveling 80 kilometers per hour toward each other. Okay, so if I'm standing on the ground, I can see two trains both moving 80 kilometers per hour toward each other. Okay? Someone standing on the tracks or standing beside the tracks or whatever, looking at these trains, would be able to see that each of them is traveling at equal speeds toward each other, right? So not in the same direction, but in opposite directions toward each other. Okay? If I was standing on one of the trains, which changes my frame of reference, right? Now I'm standing on a train that's traveling 80 kilometers per hour in this direction. There's a train coming at me 80 kilometers per hour, right? So it seems to me that that train is moving 160 kilometers per hour, right? They are covering the distance between us twice as fast now, right? My train is moving there and their train is coming. So that frame of reference changes how fast we perceive things. Okay, does that kind of make sense? All right, so if I'm going 70 miles per hour down the road and I meet someone or I come up on someone, like behind someone that's traveling 55, how fast does it feel like they are traveling? Really slow, right? Do you have that experience? You're driving, you come up on somebody that's going slower than you. Does it feel like they're going 55 or does it feel like they're going 15? 15, right? You are moving 70, that's your frame of reference. Then all of a sudden you have to slow way down. It feels like that person is crawling, okay? But realistically not, right? They're going 55. So there's just a different frame of reference depending on your velocity, depending on where you're looking, depending on other things' velocity. That's kind of what relative velocity means in general. So our frame of reference can change how we view things, how fast we see things, all that kind of stuff. Okay, does that make sense? Okay, so those were all examples of what we call same line velocity. Okay, so same line velocity means things are traveling within the same axes, right? They're both going north and south, or they're both going east and west, whatever. They're going to go in the same general direction. Okay, so all we're doing there is adding or subtracting our different velocities, right? If we're on the train and the train's coming toward us, we just added our velocities. It seems to us that that second train's moving 160 kilometers per hour. When we're both going the same direction, I'm going to end up subtracting those because it feels like they're going way, way slower. Okay, so that's same line velocity, really simple. Okay, so let's go ahead and try this one. Sam's skating 3 meters per second west. If I push him so that he ends up traveling 5.3 meters per second west, what was the speed of my push? Okay, so this is really simple, just vector addition, right? So here's Sam, he's going 3 meters per second west. I'll draw my resultant vector in a different color here, right? Resultant vectors always goes from the origin to the tip of the last vector, so my resultant is 5.3 meters per second west. Sorry, that 3 should be meters per second. Which means if I want to add tail to tip to get to my resultant vector, my push had to be at what value? Right? How fast did I have to push him? 2.3, right? That's it. Okay, if he started out moving 3 meters per second and he ends up moving 5.3, that means that extra 2.3 meters per second had to come from somewhere, which means that was the speed at which I pushed him. right? So he ends up moving 5.3 meters per second west. Okay, this is simpler than even drawing the diagram, right? I think most of you probably came to that conclusion without drawing the diagram, hopefully. That's fine. Okay, for same line velocity, it really, really is that simple. When we get to two-dimensional relative velocity, it's a little bit more complex. So if we don't have just simple addition or simple subtraction of vectors, we're going to have to use vector addition. So adding our x components, adding our y components, using the Pythagorean theorem to find our hypotenuse. Okay, so we're going to have to basically use vector addition, so adding things tail to tip to get to our resultant vector. So it's a little bit of a review here with vector addition. Okay. When we draw these diagrams and when we do relative velocities using vector addition, it's extremely important to have a diagram. Okay, so to say he went this way first, and then he went east, and then this is his result. Okay, because relative velocity problems are sometimes worded a little funky. All right, so we have to know what the resultant is, and we have to know how to correctly draw that diagram to be able to view our resultant correctly. Okay? When we draw a vector and a resultant vector, right, our other vector should always add tail to tip to get to the resultant vector. And that's a really tricky concept for us to remember when we're looking at these problems. Okay, so our resultant vector always goes from the origin to the tip of the last vector, and all of our other vectors should add tail to tip to get to that point. All right, I know I'm going to keep saying that, and you're going to get tired of hearing me say it, but it's important. Okay, this is a Microsoft PowerPoint's attempt at a boat. Okay, kind of hard to see there. A boat is attempting to drive straight across the river to get to the other side. Okay, the river is flowing at a rate of 1.2 meters per second west. The boat needs to be traveling 1.85 meters per second on its path straight across the river. What speed and at what angle must they leave the shore? Okay, so can we visualize what's happening here? Their goal is to make it straight across from where they started. But that current is going to be pushing them. Okay? So let's think about this. If I want to travel, okay, it sometimes helps to like visualize with your hand here. If I want to travel straight across west, that's going to be my resultant vector. Okay? So I'm going to start with my little boat here. And my resultant is going to be in purple. Okay, I want to end up straight across from where I started. So here I'm drawing my resultant first. Okay, this is my resultant vector, and it's 1.85 meters per second. Okay, that's my goal. I want to make it 1.85 meters per second straight across from where I started. Okay, so let's think. If I want to make it here, right, and the river is pushing me west, right, to the west, where do I need to leave to make it to my final point? Out like kind of northeast, right? So let's look at this. I need to understand that the river itself is going to push me to the west. So it's going to push me this direction, which means I need to leave out here somewhere. Okay? A lot of us will just want to draw this like this. Here's our 1.85, it's going west, so I'm going to leave over there. That doesn't make any sense, right? If I leave to the west and the current is pushing me west, there's no way I'm going to get to my final destination. Okay, so we just have to be careful when we draw these diagrams. Okay, so we can kind of visualize like this. I want to make it straight across the river, but it's going to push me west. So in order to get straight across, and it's going to push me west, that means I need to leave somewhere over here, and I'll get pushed back to where I want to be. Okay, river is flowing west at 1.2. That means we want to find how fast and at what angle we need to leave the shore. Okay, so the math that goes into relative velocities is just Pythagorean theorem and the trig functions. Drawing the diagram is by far the most difficult part. Okay, so let's go ahead and solve Pythagorean theorem here to find out how fast we need to leave the shore.
Just so I remember, the Pythagorean theorem is the number a squared is b squared equals c squared.
That's right. 2.21. Good. Okay, and then how do we solve for the angle that we need to leave at? Second anything. Realistically, we want to use the numbers they gave us, because if we missed on solving our hypotenuse, then we would have our angle wrong as well. Okay, so we want to make sure we use the numbers they gave us, which means we would use second tangent, because that's opposite and adjacent. You can use either one. It's not that big of a deal, but I'm just saying if you calculated your hypotenuse wrong, then we might be in trouble a little bit. Okay, so here is our starting point, which makes this angle what of what? Right, here's our origin, here's our crosshairs. South, east, west, and north. Okay, what is that angle then? 33 degrees. What of what? East of north. There we go. East of north. Because it touches the north axis, then we decide, does it swing east of north or west of north? Okay. So our final answer here is 2.21 meters per second at 33 degrees east of north. Okay, so this tells us the same boat leaves the shore driving straight across. He's going to let the current push him west, and we want to find out what is his velocity. So if I'm standing on the shore watching this boat, right, he's just driving across, but he's letting the current push him. Okay, so I want to see if I'm standing on the shore, where does it look like to me that he's traveling? Okay, that's what we're looking at here. Okay, so now he's heading out straight across. Is that going to be my resultant this time? No, because that's not his goal. That's not his final velocity. This is just where he's trying to go, right? So this is 1.9. The current is pushing him which way? To the west, so to the left, good. 1.45. So we want to find out what speed is he actually traveling. So this is going to be my resultant here in pink. Okay, we don't know what speed he's actually traveling at. Okay, so if I was standing on the shore, I would be seeing him kind of drift in that northwest direction. Okay, so same thing here. Find the hypotenuse and the angle. Here. 2.4 meters per second at
37 degrees west and north.
Perfect. Very good. Let's go ahead and try this one on your own. Yep, same thing. You're still going to have to draw your vector, so it's still going to make a triangle. Okay, so we had our marble, which was originally, right, even if this marble's not rolling east, It's still moving east because the boat it is sitting on is moving east. Okay, so it doesn't feel maybe like it's moving, but it is. Okay, so here's our marble. It's going to go 4 meters per second east and then 0.75 meters per second north. So that means our resultant is going to be this vector somewhere in the northeast direction. Okay, our velocity has to have magnitude and direction. So when we ask for velocity, you got to have that angle that goes with it. Okay. Keaton, what'd you have for our velocity here?
I put 4.07.
Okay, and what about the angle? Got to have both things.
10.62.
Good. 10.62 degrees. What of what?
Is it okay to like round up on a
Yeah.
north?
Yeah.
North of east?
Perfect. North of east. Very good. Okay, plane flies north, but its actual velocity is that given vector. So you are going to solve now for the speed of the wind. Okay, you're going to solve with what speed is the wind pushing that thing to get it to 243 kilometers per hour. Okay, so draw that vector. And what number? 4. What did you have? 5,400. Yeah. It does. Because that's east of north, so make sure you're drawing it east of north. Did everyone's diagram look like this? Hopefully? Yeah? Good. Good. I had about 138.4 meters per second. What? 138.4 meters per second. What's our direction here? East. Due east.
Wait, isn't it kilometers per hour?
Kilometers per hour, I'm sorry. All right, very good.